Okay, Assalamualaikum and salam sejahtera. So kita akan membicarakan tentang tutorial 8. So in tutorial 8 here, we have a uniform compressible flow occurs in a constant diameter pipe. So write the simplified differential continuity equation for the steady flow. So kita nak cuba, we try to write what is the differential continuity equation for this one. So we have a pipe wall here. So in this situation, so the difference is the wall here is not moving, but the fluid is moving from left to the right like this one. Okay, so in tutorial number 7, the fluid is flowing downward, so means that the element of gravity must be there. So in this situation, the gravity is actually not influence the flow because gravity will only act on y-axis. So I think I could go a little bit faster because you already know the tricks. So the rule of thumb is you try to simplify the Navier-Stokes equation or the continuity equation by using all the assumptions that you can make from the question. So for example, this is the continuity equation that we learned previously. And then because we have a few conditions like this one, as stated here, we could simplify as d rho over dt. Because it is a steady flow, so means that the density is not changed with time, everything is not changed in time. So that is the definition of steady flow. And then because we are only focusing on the x-axis, so might be we don't have du dx here, so the value of u and the value of w is equal to 0. So we have the dv v equal to 0 and w is also equal to 0. So, and then finally, we could have this term. So, because we take lesson from tutorial number 7, because in tutorial number 7, we don't know the situation, whether it is compressible or incompressible. So, that's why it is advantage for us to leave the value of rho here is not equal to, the rho is, we let the rho appear in the equation. Okay, so I hope you could see this after this class. So for tutorial number 9, for example, we have this one, an incompressible flow of air over the mountain range as shown below can be approximated by a plane steady flow. If the z-axis is vertical and density is allowed to vary, so means that the density can be changing, write the differential equation that result from conservation of mass consideration. So conservation of mass here is actually reflect the continuity equation. So let's say we have the incompressible flow and steady flow here. So why we take incompressible flow here? Because this is actually the situation. Normally, if we have a pipe here, so it is a closed conduit area. So means if the flow, the pressure cannot release, so it can be compressed. Okay. However, if we have a big situation like this one, a very large area, a mountain and so on, so we assume, yes, in real application, we found that the pressure at here and pressure at here might be largely different. Okay, and then the density here and density here might be different. Okay, so this is the real situation if you climb a mountain. But the idea that we need to take is if it is open. So however, this condition is actually open. We don't have a boundary. So we don't assume that we have a great wall here and another great wall here, because it is a very large scale of natural phenomenon. So in this situation, so might be we could assume that the air here is incompressible. So I hope you could imagine the situation in this question. So because it is a steady flow, so and then the density is not changed with time, so it is also stated in the question as incompressible air. So we assume that d rho dt is equal to 0. So means that there is no changes of density along the time. And then because we assume that we are focusing on the z axis here. Okay, so means that for this one, we have this is the z axis, this is the x, and this is the y actually. Y is actually normal to the screen. So maksudnya apa nama tu, y adalah yang serenjang, yang perpendicular dengan screen komputer awak. So saya harap awak dapat faham yang itu. Jadi kita kata there are no component of y, that's why we take d dy is equal to 0 because we don't have any we're not dealing with any y element. Okay. So and then we could simplify our continuity equation like this one. So this is our continuity equation. So we could simplify it into this one. So and then we could expand the terms become this one. So here, okay, so might be it's a little bit different because we have del rho u over dx and so on and so forth. So this is actually, if you expand this one, actually you could get the term of this one. Okay, I just to show you the variation that you could write this one. So the first one is, this is actually the term of continuity equation which not expand yet. So another thing is, okay, in some situation we take rho u here because maybe, okay, we assume that the density is changes and also the velocity is also changes. So this is the especially for the compressible condition. Okay, so please, okay, we leave it this one. So and then if we expand this term, so we could write this one. I hope you could know how to expand the partial differential terms into this term. So and then because we are dealing with incompressible, so we assume that d rho dx and d rho dz is also equal to 0. So and then we zero the value of d rho dx here and also d rho dz. Okay, so again you must know what is the meaning of d rho dz, and because if you are misunderstood about the rho dz is equal to 0, you may zero the value of this rho. Okay, rho is constant, so means rho must have a value. Okay, density constant membawa maksud density tidak berubah, bukan density kosong. Okay, please remember that. So means the incompressible means that the value of density is constant. So means the rho here must have value, and because the density is constant, density tidak berubah, so means that d rho dz and d rho dx will also 0. Means the gradient, the changes of density along the x and along the z axis is 0. Okay, so I hope you could understand the meaning of d rho dx equal to 0 and why the value of rho here is not equal to 0. Okay. So and then we could simplify this term after we neglecting the value of 0, the value of d rho dz and d rho dx, and then our incompressible continuity equation will become like this. So and then we could simplify, okay, we could bring the rho to the right hand side, so we have this term. So here, so this is the mathematical terms. Please understand that we are not assume as the density is 0. So what actually happened here is, if we factorize the value of rho, we could write rho, okay, du dx plus dw dz here is equal to 0. So for this situation, we have, normally in mathematical expression, we could say we have two conditions. One is rho is equal to 0. or we have the total of du dx plus dw dz is equal to 0. But in reality, we could say that rho is totally cannot equal to 0. If rho density is equal to 0 means there are no element, there are no fluid, there are no mass on that on that location. Okay, so means that the only parameter that can be 0 is actually dx dz, du dx plus dw dz. So this is a plus symbol. So if the velocity is negative, so we could achieve the value of 0. Okay, saya harap awak dapat faham yang ini, kerana kadang-kala berlaku kesilapan, kerana berlaku silap faham dengan perkataan density density is constant. So kita pergi kepada tutorial 9B ni saya tidak saya tidak bincangkan lah. Okay, kita pergi kepada tutorial 10. So in tutorial 10, so consider steady, inviscid, incompressible uniform flow in a two-dimensional diverging channel as shown in figure. The inclined walls of the channel are straight and the fluid enters the diverging section with velocity v1 equal 40 meter per second, given h is equal to 1 meter. And assume 1 unit width. So 1 unit width here means we assume that the width is equal to 1. Okay, kita anggap bahawa lebar dia adalah sama dengan 1 unit ataupun 1 meter. So the question is determine an expression for the velocity component u as a function of position x along the channel. U does not depend on y. So and then we need to calculate and determine an expression for the acceleration of the fluid in x direction. So kita ada satu keadaan seperti ini. We have a converging diverging. So we have a section like this one, and the problem is at this section the width or the channel here expand the cross-sectional its cross-sectional area. So means that we need to calculate what is the equation that could express the increment of this cross-sectional area. Okay, why it is important? Because when we want to calculate a flow rate, so Q is equal to AV, so we need to know the value of cross-sectional area. So we answer question A. So determine an expression for the velocity component u as a function of position x along the channel, and we assume that u does not depend on y. So the question here is asking us to calculate, to determine expression mean equation. So equation for velocity component u, so means the velocity that moving on x direction. So what is the equation for this velocity? Okay, so it is u as a function of position x. So mean we need to write an equation. What is u in the function of x? So this is the question. So and then in this question is not given. The assumption is not given, but normally you may come with your own assumption. Okay, the common assumption is for sure it is a steady flow, because if steady flow means all the parameter is remain constant at any time. Okay, so and then it is inviscid flow. So inviscid flow mean flow which is not influenced by viscosity. So because after this we will enter ideal flow. I think I already described this one in the first meeting. So inviscid flow means flow that's not influenced by viscosity. So means there are no resistance comes from the fluid itself. So and then it is incompressible flow. Okay, because in our syllabus actually we are focusing in incompressible flow. Okay, but at the last topic, at the last chapter, we will describe about compressible flow. Okay, so that is the only chapter that describe the compressible flow. So another reason is we cannot use Bernoulli equation to calculate compressible flow. So means that your knowledge about how to calculate the flow, the velocity, the pressure is actually not ready for compressible flow problems. So that's why we take care of that situation. Almost all the situation is incompressible flow. So and then it is a uniform flow. And to make our calculation easier, we could take it is as two-dimensional. Okay, it is also reflect with the idea of a unit width. So because the width is 1 unit, so it means that we simplify the Z axis. So kita tak nak ada banyak axis. So kita anggap paksi Z ataupun paksi lebar adalah satu unit sahaja. Dan kita hanya membicarakan paksi X dan paksi Y. Okay. So ini adalah this is a few assumption that you could use to solve this problem. And this assumption is actually is made by yourself. So maksudnya awak propose proposal, awak propose idea, awak propose condition apa yang sesuai, yang commonly digunakan untuk menyelesaikan keadaan ini. Okay, selalunya inilah parameter yang awak boleh keluarkan. Kalau awak boleh keluarkan semua parameter ni, insyaAllah tak ada salah lah. So maknanya kita selalunya pihak kami akan menerima dengan mudah. Kerana inilah juga assumption yang kami gunakan dalam research yang melibatkan pengiraan flow rate dan sebagainya. Okay. So first, we need to calculate the volume flow rate at inlet. So volume flow rate, so from fluid mechanics 1, I think you already know to calculate the volume flow rate. So it is A times V. A here is 1 meter times 1 meter because we assume that the H here is 1 meter according to the question, and the width here is also 1 unit meter, one unit. So it is 1 times 1. And the velocity for V1 is given in the question as 40 meters square, 40 meter per second. So you could assume that the flow rate entering this device, okay, it is equal to 40 meter cube per second. So and then, as I said, because the flow rate is influenced by the value of A. So now we found that the A at this point and the cross-sectional area A at this point is totally different. So we need to calculate what is the different, how the difference change, how that value change. Or we need to create an equation to reflect the cross-sectional area. So we know that if the value here is hx, mean the value of hx here means the value of h is changed according to x axis. Nilai h akan berubah sepanjang paksi x. Okay, jadi we could write the A here, okay, the cross-sectional area can be assumed equal to 2 times hx, maknanya 2 darab hx here, mean the total height of this one, and time width. Okay, because width is equal to 1 unit, so we could say that A here is 2hx. And please understand that h bracket x here, it doesn't mean h times x. It means that h is a function of x. Awak jangan silap faham. Hx di situ sebenarnya adalah satu term saja, iaitu nilai h. Tetapi kenapa kita tulis hx? Kerana h berubah dengan nilai x. So awak kena faham. Sama juga kita tulis y sama dengan mx campur c. Sometimes in a certain textbook they will write yx is equal to mx plus c. So this is the situation. Okay, so what we need to do is we need to determine the changes. Kita kena create equation yang menunjukkan perubahan tersebut. Jadi macam mana yang kita nak buat? So from the question we know that these changes is actually showing the linear correlation. Okay, dia bukanlah apa nama tu, exponential ataupun kuasa 2, kuasa 3, dia adalah linear. So kita tahu bahawa linear ialah y is equal to mx plus c. So what you need to do is you need to draw a graph and then you need to come out what is the value atau or what is the function of graph that you have. So means that we draw y-axis here as hx and the x-axis here. So at this point, okay, so the coordinate here is 0 and 0.5. So you know that the distance here is 1. So if this is the x-axis, the center point, so it will become 0.5. And here, so we have 10 and 2. Okay, so why? Because it is given in the question that h is equal to 1. So we have the total height is 4. So mean the distance from the center point here is actually equal to 2. So we have 2h. So we get 10 here. And we have 10h here. So we have 10, 2 here as the coordinate for the second point. So by using this point, I think you could come out with the velocity with the equation of y mx plus c. So finally, we could have the equation is hx is equal 0.15x plus 0.5. So I will not explain about this. So I think you already know how to get this equation. So and then what we need to do is we need to determine the velocity. So according to the continuity equation, u is equal to q is equal to a and u. Okay, we just replace the value of v with u because we are focusing on the u velocity, only velocity that move on x-axis. So we could write we could write u is equal to q times q divided by a. So and then we replace the value of a here with the equation that we have here. So again, you must know that this is the value of hx. So means to get the value of a, we need to multiply the value of hx with 2. Okay, so this is the idea. We multiply with 2 and then we times with 1. 1 here is the width. Okay, because the width is only 1 unit, so we could simplify it as a 2 times h. So, and then we could simplify the term, so we could get this term. So this is the equation for the velocity along the x-axis. So and then we need to determine an expression for the acceleration of the fluid in x direction. So the acceleration is shown in the previous slide. So I think I show you how to determine the acceleration. So this is the acceleration for x-axis. So we have du dt plus u du dx plus b du dy plus w du dz. And then because it is a steady flow, and then we only focus on x direction, so we could simplify the equation here. So we only have acceleration for x, it is equal to u du dx. Okay, so and then I'm sorry, so I'm copy paste too much. So and then we know that the value of u is 20 over 0.15x plus 0.5. So you know that we could use this equation to find what is the value of du dx. So and then if you calculate the value of du dx, okay, so this is the method that you may use. So because it is not easy to differentiate that term, so we simplified into, let's say s is equal 0.15x plus 0.5. So instead of we have, so from here, so we have ds dx can be is equal to 0.15. So and then here we replace this term into s. So means that we could write u is equal 20 over s and du ds is equal to negative 20 over s square. Okay, and then we use this method. So we say that du dx can be solved by multiply du ds times ds dx. So we substitute the value of du ds and ds dx, and finally we could get this value representing the value of du dx. So now we have the acceleration u times du dx. So we substitute the value of u here, and then we substitute the value of du dx, and finally we could get the acceleration for x-axis can be represented as this term, minus 60 over 0.15x times 0.5 by the power of 3. Okay, let's say we are dealing with same question. So, but we need to calculate, we need to determine the expression for the velocity in y component, in v component, and also the expression for the acceleration in y direction. So, in previous question, we are calculating the x-axis. Now we are calculating the y-axis. Okay, so you could do this because the idea is the same. So instead of we are focusing on x, we are focusing on v, on y. So and then this is the continuity equation, and then we could write as dv dy is equal minus du dx. So and then we integrate both sides. So and then we could write as from here. Okay. Okay, here, so the difference of this solution is previously in this question, we use the changes of this one to determine the value of u. Okay. Okay. But in this situation, in second question, by hook or by crook, we need to get the value or the expression of the v, of the velocity v. So we cannot do as previous solution because it is not quite related between the cross-sectional area and the V. Okay, as I said, if you have pipe here, the velocity here and this proportional or the perpendicular cross-sectional area will give you a flow rate Q. But if you have V here, so this V is not perpendicular to the cross-sectional of that pipe, of that object. So means you cannot simply say that the flow rate is equal to V times this area. So it is totally wrong. So that's why in this situation, we need to do this method to get the value of V. So what we do is we do the integral method. So it is very simple. So we have this one. So the simple one is if we bring dy here, so we have dy here, and then if we integrate this, I'm sorry, not here, we integrate both sides, so we could get this term. So and then again, we integrate dv here, we'll get v. So and then if we integrate du dx over dy here, okay, so we have integration of du dx dy. So it is just the integration of the integration of the differential terms. Maksudnya that awak kamirkan sesuatu yang di dalam bentuk pembezaan, so dia akan dapat dirinya sendiri. So jadi kita akan dapat du dx sahaja sebenarnya. Okay, so and then kita akan dapat du dx dan juga kita akan dapat du dx dan juga c, iaitu constant. So and then, okay, the problem is, so the du dx here, okay, is actually can be replaced by the previous equation. So why we can replace with the previous equation? Because we are analyzing the same objek. Kita menganalisa sesuatu objek yang sama, oleh itu kita boleh pakai nilai yang telah kita dapat dari pengiraan terdahulu. Jadi apa yang kita dapat di sini ialah kita kata integration of V, integration du dx dy plus C. So kita kata kita masukkan nilai du dx, we substitute the value of du dx here with the previous term. So and then we integrate by using dy. So we could have, because we don't have any y terms in this term, so it is become 3y over 0.15x plus 0.5 square plus constant. So and then this constant need to be determined. Okay, please be careful. If you have constant from the integral, okay, please determine the constant from the boundary condition. So because I think a few questions from our tutorial is showing how to calculate the constant from the boundary condition. So what is the boundary condition? Boundary condition means the condition at the boundary. Satu keadaan di sempadan di antara cecair dan juga solid. Okay, jadi dalam keadaan ini kita boleh beranggapan bahawa pada ketinggian y sama dengan kosong, okay, had laju v juga kosong. So jadi when we substitute these terms, we could get that x0 and y0, so the value of c will become 0. So and then we could write that the velocity here, the velocity at v, the velocity v can be written as this one. So why we write in bracket xy here? Because the velocity of v is actually dependence on the location of x and location of y. So means that v with function of x and y can be written as this one. Okay, so I hope you could understand this solution. So means that this is the expression, the expression of the velocity for v. So and then we try to come out the expression of the acceleration in y direction. So this is the expression of acceleration in the x, and this is the second one here is the acceleration for y direction. So it's you just if you see the equation, you just replace the element of x here with the element of y. So and then because the width is equal to 1, okay, we just assume that there are no influence of z direction. So we could neglect this term. So we have this one. So and then we cannot neglect the value of u and v, because in our equation here, so we have x and y. So means that the location of x will give you u, will give you velocity u, and the location of y is actually will show it is showing the dominance of v. And what we need to do is we need to substitute these four items. What is u, dv dx, and what is v, and what is dv dy. So we could calculate this by using previous equation. So previous one, we have u as this term. So and then from the current calculation, we get v as this term. So we could calculate that dv dx is this one, and dv dy as this one. So and then how to get the dv dx, you can refer to the previous solution. Okay, you could assume that this term, the bottom one is equal to s, or equal to a, equal to b. So and then you could do the differential process. Okay. So and then we could calculate the acceleration, okay, by substituting all the parameter here. Okay. So and then finally you could get the acceleration at y can be expressed as minus 9y over 0.15x plus 0.5 by the power of 4. So this is tutorial number 11. A fluid in between the plate shown below flows flows when top plate is moved with a constant velocity u. So starting with the simplified expression above, determine an expression for the velocity profile with appropriate boundary condition. So in this situation, so we have a horizontal situation like this one. We have two plates. One, the bottom plates here is not moving, so u is equal to 0. And the top bottom here is moving at certain amount of velocity. So we have u. And between these two plates, so we have a fluid here. So and then we need to determine the velocity profile. So velocity profile means u is equal to what kind of equation that we could express the velocity profile. So another thing that you should know here is how to draw the velocity distribution. So I think in fluid mechanics 1, you learn about the no slip condition. So means that if you have a molecule here, so this molecule will stick very hard on this surface, so the velocity is equal to 0. That's why in boundary condition, we assume at this situation, u is equal to 0 at y equal to 0. And actually, at this top plate, the molecule here is stick very well too. It stick very hard and it's not moving. So the velocity, because it is stick very hard on this top plate, so the velocity is equal to 0 also. But, okay, because this top plate is moving at certain velocity, so we assume that kita melihat secara relatifnya, kita dapati bahawa sekiranya top plate ini bergerak dengan certain velocity, oleh itu molekul di sini juga akan bergerak dengan velocity yang sama. So jadi kita kata that's why kalau melukis velocity distribution, kita boleh melukis bentuk ini. So this is the diagram of the velocity distribution. So we assume that this molecule's velocity is equal to 0, but this molecule actually moving at u is equal of u here. Okay, saya harap awak dapat faham yang itu. Jangan terkeliru dengan sifat molekul berdalih yang mempunyai sifat no slip condition. So sekiranya awak belajar master nanti, kita akan melihat satu situasi di mana no slip situation berkurang dengan certain percentage. Itu kemudian lah. Di dalam fluid mechanics 1 dan fluid mechanics 2, kita membuat anggapan mudah bahawa no slip condition berlaku, oleh itu had laju molekul yang melekat pada sesuatu solid selalunya akan bersama dengan kosong. So and then here I simplified everything. So means that you need to start with the Navier-Stokes equation on x-axis, and then you give all the simplification. It is steady, uniform, incompressible, and so on and so forth. And finally, you could have the velocity profile is actually u equals c1y plus c2. Okay, so saya simplifikan everything. Okay, awak boleh refer kepada nota yang terdahulu yang membicarakan tentang dua plate seperti ini, satu bergerak ke sana dan satu bergerak ke sana. It is actually telling you the same things. Okay, so awak refer balik nota yang itu. And finally, we could say that the general equation for that situation, for this situation, is u equals c1y plus c2. And then we are using boundary condition like this one. Okay, so means that at this one, y equal to 0, u is equal to 0. And at this point, y is equal to h and u is equal to capital U. Okay, so that's why I write here is a capital U, just to differentiate between small and capital U. So and then if you substitute the boundary condition here, so you will get the C2 here is equal to 0, and then you will get C1 here is equal to U over H. That's why you could write the U function of Y is equal to U over H times Y.